So now we'll start on Fourier analysis on Z2 to the n. Yeah. One second. So I did something very stupid. Just now so misplaced the tablet pen. Hold on. Found it. Okay, so we'll do Fourier analysis on Z2 to the n. So of course, from Fourier analysis of Zn, we already had got the characters and everything for Z2 to the n. But let's do a quick recap of what they were. Right. So what is the group is here. Z2 to the n, which we can regard as -1, 1 to the power n. And this is multiplication, right? So 1 into 1 is 1, 1 into -1 is -1. I mean, the usual. So that is the way I write it. And then what was G hat? So what were the homomorphisms here? They were of this form. I denoted them chi s. S indexed by subsets of 1 up to n. This is the set 1 up to n. These were indexed by that. And what were they? Chi s of x is product. Maybe I try to write small x here. Xi I in s. See, you take one, I mean, so if you map x to xi, that is a homomorphism. It's clear. This is a product group. So x to xi is a homomorphism, and xi will be plus or minus 1. So if you take a product over I in some subset, that also will give you a homomorphism. If you take x and y, then it's clear it's homomorphisms. And these are all the homomorphisms into the circle group. Okay, so these are the characters. So these are all the characters. And then, of course, if you have a function, then its Fourier coefficients are, since we usually do divide by the size of the group, square root of the size of the group, f inner product chi s, because it is chi s over square root of the size of the group, which is so the size n here is 2 to the small n. So this is what these are the Fourier coefficients. Yeah, okay. Anyway, so this is yeah, I don't need to write what it is. So and then you can write f as 1 by f hat of s chi s of x. F of x is or subsets of n. Okay, so this is what Fourier. So these are the Fourier coefficients. And this is the expansion. So if you yeah, that's all. Okay. So and the Planck-Chagall formula will say that if you take sum of fx square, that will be the same as sum of f hat of s square. So this is the Planck-Chagall. I think in the notes I also indicated how you can arrive at this without any group business actually. So one other way of thinking of it is these are, you see, these are polynomials in Xi. Chi s is a polynomial of, think of X as variables, then Chi s is actually a polynomial. In fact, it is a multilinear polynomial. By multilinear, we mean it's linear in each variable, which it would be because here xi square is xi, right? In our group, xi square is xi. So there's no point taking anything to a higher power. Any power, either if you have any polynomial of x1, x2, xn, and you want to evaluate it on this z2 to the n, then higher powers are useless. The only thing that matters is whether the power is odd or even. So you might, all polynomials are multilinear polynomials, and
So,
this is
Manju, in your minus 1 1 notation, then xi squared x that is in 0 1, right? Here,
sorry, xi square is 1.
yeah.
Oh, yeah. So I should say xi square is 1. Therefore, you can leave it out. Yeah, you're right. Xi square is not xi square is 1. So higher powers are not, yeah, it's not minus, it's not the parity, but yeah. So xi cube is same as xi power 4 is 1, etc. So any higher power can be replaced by either 1, in which case it doesn't depend on xi, or xi itself. So all polynomials of relevance will be anyway multilinear polynomials. So I have indicated somewhere, I think, how you can just start with that idea, and you just expand any function, you can directly arrive at something like this. Okay, so that's just one way of saying it. Okay, so this is the basic Fourier analysis of Z2 to the n. So there are some other special concepts which I have not introduced in general. I am not even sure they make sense in general, but which are useful here. I don't know how much, to what extent I need all of them, but let me anyway introduce them. Okay, they are useful things to know. There is a lot to this. By the way, everything I do here, a good reference is the reference for everything I do on Z2 and Boolean functions is this book by Ryan O'Donnell called Analysis of Boolean Functions. So he's a computer scientist, and it is essentially a book written in that form, but it's completely readable. But there are many aspects to it. There are many computer science applications and other things and so on. So I'm going to extract a very small concrete part of it so that self-contained application can be done here. Okay. So this whole business also has recently been important in probability, but again, I cannot give applications from there. Firstly, I am not expert in these, but secondly, the thing is, if you don't know already sufficient amount of that probability, then it might not make much sense. So what I'm trying to go give is a self-contained application. That's my aim, which hopefully will you will still feel is of interest. Okay, I mean, so in itself it should look interesting. Okay, so this is there. So now let me introduce some concepts. Okay, so some concepts which are maybe not there in full generality, but we'll use here. So discrete derivative. Incidentally, a lot of times functions which are taking values in -1 1, they will show up. So maybe I just define them. if f is from z2 to the n to a 2-point space, which we can take to be minus 1, 1 or 0, 1, anything. I mean, 2-point space is f is called a Boolean function. It takes only two values. So the way the application will show and all this, the interpretation will be like this. Okay, so maybe I give the interpretation here. So there are, you think of them as n voters. So these are voters. And then there are two candidates. Okay, so +1 and -1 are two candidates. Who are standing for an election. So each of them, so if I take an x in z2 to the n, so it will have either, so just writing plus for +1 and minus for -1, plus, minus, minus, plus, plus. So let me just close the door. There is a lot of noise. Hold on. Yeah, so the way x, any particular x, you can think of as a voting pattern, meaning here first voter is voting for +1, second voter is voting for -1, and so on. Okay, so people can all vote, and then how is it combined to form a choose who is going to be decided? A Boolean function has to be used. Okay, Boolean function will be used to decide how to combine these votes to choose which candidate will be in office. Okay, so of course, the natural democratic one would be just to choose majority. But there are many other interesting Boolean functions also. So, for example, there is something called recursive majority. So, where just to mention a function which I have not mentioned before, it's not that we will do anything with it, but you can imagine that the whole country is divided into maybe some number of states, let us say 3 states. Odd number, I prefer odd number. Even when taking majority, when it is even, then there is a problem. So let's assume then that it is odd. So let's say the country is divided into 3 states and each state is divided into 3 cities. So you can maybe go on for further. Maybe cities are divided into constituencies and so on. But for a moment, let me stay at this. So then, and in each of these, there are a certain number of voters, let us say. So this is nation, this is state, city, and let's say here I have voters directly. Okay, maybe there are a certain number of voters here. I have written 5 voters here and so on. So these are the people who vote. But instead of taking a direct majority of all the voters in the country, the way it will be decided is, suppose these 5 voters vote like this, then in the city is voting plus, because you will take the majority of the voters in the city, and that will, the city's decision is a plus. Maybe another city will, you take the majority within that, and then that city will decide minus, and so on. Now each city in the state will look at the 3 states, 3 cities in the state. Maybe 2 states, 2 cities vote minus and 1 city votes plus. Then this will be a minus. Okay, and similarly for each state we arrive at the decision. Maybe this state votes plus, this state votes plus. Now to decide the overall who wins, so you take the majority in the states. In this case, it turns out to be plus. So this is called a recursive majority. It is an interesting and realistic type of thing one might want to analyze in terms of in this voting context. But so majority is one, dictatorial function is one where everyone votes, but so f of x is x1. So that's a dictator function. Meaning whatever the first voter says goes. Okay. So more generally, you may have f of x is, let's say, majority of x1, x2, x3. Although n may be very large. That means there is some Politburo like thing. So there are some three fellows who control everything. So that's the type of. So there are many Boolean functions of interest. And the application that I'm going to give will be of to this voting type question also. Okay. Anyway, so coming back here, so just to introduce some of the concepts. So functions which take values in -1, 1 will be called Boolean functions. We will concentrate on them, but when I'll stay general when not needed to concentrate on that. Okay, so first concept that I want to introduce is discrete derivative. Discrete derivative. So fix any.
One question,
Yeah.
Manjunath. So
Yes.
maybe this is sort of explicitly outside the purview, but when you look at Boolean functions, there is both and or. And I don't know if both operations are sort of considered in this homomorphism here.
Mm-hmm.
Because
no, and is and I mean if you take and of x1, x2, xn, it is just what I mean. Okay, hold on. In this case, so when you say and, it means if all of them have to be one. Yeah. So and function means if even one coordinate is -1, then it is -1. Otherwise, it is 1. Right.
correct.
Okay, it depends on how we map. Actually, let's be clear. So let's say we map -1. Okay, 1 we map to maybe 0. Actually, sorry. Because that's the identity. So the other way of representing Z2 is 0, 1. And this our way of representing it as -1, 1. But the identity, since the identity is 1, let me map it 1 to 0 and -1 to 1. Okay. So your AND function here, if just because I understand here, AND function means AND of x means it is 1 if xi's are all equal to 1. That's all. Right. And all of x is 1 if even one xi equal to 1.
Correct.
So these functions are not and 0 otherwise. So these functions are not characters actually. So if you take these functions are not characters. For example, if I mean it's kind of easy to see. If you take any two things and check, homomorphism is not satisfied. So, but you can lots of Boolean functions you can write in terms of them, and that is important. But
I see. So these can be represented using these characters, but they are not themselves characters, right?
no, they are not themselves characters. Yeah. So that is one. So each of them is 1 on exactly one coordinate and 0 elsewhere. And even if you transfer it to 1 minus 1, that is not going to give a homomorphism as far as I see. Yeah. So that's not, those are not characters. Yeah, you can represent them in characters. Yeah. So definitely. Yeah. For example, yeah. Okay. Maybe since you asked this, let's just take the So let's take f of x is what is it? I want it to be, let's say, the AND function. So I want it 1 if and -1 otherwise. So this is the AND function. Just transfer to 1 minus 1. Okay.
Don't you want it -1 if xi equals?
Yeah. I mean, in the target space, I will call it 1 and minus. If you want, I can do that. It's not a problem.
Can you call it the NAND function then?
Well, okay. So in the okay. So if you, yeah, no, I don't mind changing that. So if you want, it will not make a difference for the. Okay. So let's call it 1 and 2. Okay. So let's say fx is -1 if all xi's are -1 and 1 otherwise. So how do you write it as a polynomial? Oh, let's make it 0. I mean, so actually, so the target space should not be confused necessarily with the this one. So from that point of view, let me just make it actually maybe even 0 and 1. Okay, it's a Boolean function if you want. So just
Product of 1 plus xi?
yeah, so it is just a product of 1 plus xi. If even 1 minus xi or 1, sorry, that's the same. 1 plus xi will divided by, no, something is.
So 1 minus xi over 2 product of that.
Minus, yeah, 1 minus, right, 1 minus xi, sorry, 1 minus xi over, yes. Over 2 to the n. So if all xi's are -1, this will give me 2 to the n and it becomes 1. And if even one xi is 1, then this will be 0. So now you can expand it by binomial expansion. So what you get is sum over all subsets of n -1 to the size of s product xi I in s. So this is chi s of s. So you see that f hat of s is actually -1 to the cardinality of s over 2 to the n by 2. Since I wanted to write the expansion, I would like to, yeah, because in my Fourier expansion, I write f as 1 over 2 to the n by 2 times this sum. So it's clear that I should take 1 2 to the n by 2 here, and this is for all s. Is this okay? So this is how you expand that function. So you can try the other one. It's something similar for 1 plus xi. So the dictator. So maybe then maybe these examples are actually useful. So let's just do a couple of them. So another example is, so let's take fx equal to x1. So what is this? What is its Fourier coefficient?
The subset x1 has 1 and everything else has 0.
F hat of s will be 1 by 2 to the n by 2, right? If s equal to the singleton 1 and 0 otherwise. So whereas if you take something like, let's take fx to be some, let's say some symmetric polynomial like a x1 plus up to xn plus b sum over all pairs xi xj.
Would it be 2 to the n by 2 if s is singleton?
Oh, sorry. Yeah, f hat of s is the inner product with no, f inner product chi s divided by 2 to the n by 2. So this chi s, yeah, no, it is, I think, 1 by 2 to the n by 2. So I'm not using the, yeah, so this is right. Yes, yes. Am I right, or is it 2 to the n by 2? F inner product. Oh, hold on. What is F inner product chi s? Okay, hold on. Yeah, you may be right. Sorry. So F inner product chi 1 will be sum over x in Z2n f of x, which will be just x1 square 1. So that will give me 2 to the n. Yeah, so when I divide by that, you are right, of course. So it is 1 by 2 to, not 1 by, it is 2 to the n by 2. Yeah, the Plancherel also should say, yeah, that's correct. Thanks. So this is 2 to the n by 2. So suppose you have a polynomial like this, a times x1 plus up to xn and b times summation xi xj. Then we will have f hat of s will be 0 unless cardinality s is 1 or 2. And you can figure out when s is 1, it will be a, maybe multiplied by 2 to the n by 2 or something else. And similarly, for when cardinality s is 2, you will have b times some number, and rest of it will be 0. An interesting exercise, not trivial at all, is to take, let's say, n is 2m plus 1. You can take it as a challenging exercise. F of x is doable, definitely. Majority of x. Okay, so that is if more of the coordinates are 1 and minus 1 otherwise. So then what are the Fourier coefficients of this function?
So can you explain the previous example again? I didn't get the cardinality of s equals 1 or 2 thing.
Oh, this one here. So I'm just saying that. So this one is so this is a polynomial. That's it. So x1 plus up to xn and b times summation xi xj I less than j. So I'm just saying that if you take this is already in the form. So this is already been expanded in. So you can this is already the Fourier expansion more or less, except you just take the 1 by, so you can take 1 by 2 to the n by 2 sum over s with cardinality s equal to 1, a times 2 to the n by 2 into, right? I mean, x1 is just the chi s with s equal to singleton 1. So this is already, these are the chi 1. You have expanded it in terms of chi 1 plus up to chi n. And here these are chi ij's. That's what that is. So you have expanded your function in terms of the singleton chi's and the doubleton chi's. So those are the only Fourier coefficients which are there. So I'm making a trivial statement. That's all. Is it clear?
Yes.
Yeah. So it's the expansion already. It's already giving the Fourier expansion, and it's using only subsets of size 1 and 2. So in some sense, that tells you what these Fourier coefficients. If you have some intuition for what these Boolean functions are like, then this is so whether the Fourier so in many applications, what matters is whether Fourier coefficients are supported on small size subsets or large size subsets. For example, if you take the product x1, x2, xn.
Shouldn't you write f hat of s is 0 when size of s is not 1 or 2?
This is supposed to be unless it's
Oh,
not.
that,
Sorry.
that is why I was confused.
Oh, okay. Sorry. Yeah, I unless size of S is 1 or 2. Yeah. That's right. So it's other things are 0. These ones are non-zero. So if you take this function, the product of all the xi's, in some sense, it's a highly unstable function, and that one has Fourier coefficient supported on. It is itself a character. It is chi s with s equal to the full set actually. So its Fourier coefficient has only one non-zero Fourier coefficient, namely s equal to the full set, and all the other Fourier coefficients are 0. This one is Fourier coefficient is supported on large size subsets. Okay. Okay. So maybe that gives a few examples.
Why do you say it's unstable? Like changing one changes the value?
Yeah, that's what it is. So there is a definition. I may introduce it later. We will not actually do much with it. Yeah. So anybody changes their mind, this will completely change. So in some sense, just I'm now not making a mathematical statement, but at the level of intuitively, if you use this as the voting thing, that means you are going to take all their votes and then take the product as the vote. Then even if one person changes his or her mind, this final decision changes. But think of something like the majority. So you have taken the majority of the votes. If one person changes the vote, will the majority change? Well, for that to happen, it has to be very tightly balanced in the first place, and that vote has to change it. So yeah, so that happens only if the winning candidate was winning by exactly one vote when n is odd, right? So in some sense that seems unlikely. So this is in some way unstable and this is stable. In fact, one of the main applications done in O'Donnell's book, in fact it's a theorem that he and some collaborators proved, is there was a general conjecture in this social choice area that majority is the stablest. In some intuitive sense, you may believe that that is somehow the least susceptible to change, but so they proved such a theorem actually. So we will not go into that. Okay, so this gives, so this majority finding the Fourier coefficients is a kind of good problem. Someone who wants a challenge can try that. Okay, now let me come back. I erased it twice, so now I'll do it. Yeah, so this is what is it? This discrete derivative. So let J be any of the voters. Okay, so okay, this is not necessarily a Boolean function. F is a function from this. So the discrete derivative is defined like this: dj f of x is you take f at, you fix all the other coordinates x j minus 1. J coordinate is 1, j plus 1 xn. So these xi's are coming from this x, of course. Okay, minus what if that particular coordinate is set to the other possible value, which is in this case minus 1. There is a little bit of static noise. Maybe somebody has microphone on. So let's take the difference and then that's yeah. So 1 second. So how do I want to define it? Half of it. Okay. So this is the discrete derivative of the function at the point jth with respect to the jth coordinate at x. Okay. So in some sense, it is what it is saying is whether how much does it change based on the jth coordinate. That's how the usual derivative idea is also, right?
But
So
is there a minus somewhere? Because what if xj is -1? Then you want it to be the other way around, right?
The way, okay, it's a good point. So the way it is defined here, it doesn't depend at all on the, no, you are, yeah, you could do it that way, but it is not that way. So the way it is done, it is this doesn't depend on xj at all.
I see.
It is just saying that if all the other voters are fixing, then what is the change if this voter changes from -1 to +1? How much is the change divided by 2? Yeah, the way it is defined, it does depend on other xi. So in some sense, it measures how much the xj is influencing. So one can put together. So this is a measure of how much the jth voter matters to some extent, right? So if it was a Boolean function, okay, I'll come to the Boolean function case, but maybe I define one more concept. Let's say if f is Boolean, then dj f of x is either 1 or 0. Okay. And this is if value of f changes. Okay, how do I say it? I mean, see, let me just say in words. So if so, when is this? It's what? Okay, it could also it could be -1 also. Sorry, it could be plus or minus. It could also be -1. So this is if jth voters vote changes the decision. When others being fixed. And 0 otherwise. So 0 otherwise. So for Boolean functions, it is that. So in some sense, this is measuring the importance of the jth voter. So one can put, but that depends on x. So we can get an overall measure of the influence of the jth voter.
Manju, you have a 1/2 there. DJ.
No, but that difference will be 2, right? My Boolean function is ±1. If
Oh, okay. Boolean, I thought 0, 1. Okay. Thanks.
yeah, so no, I said both, but thanks. So I said both, but here I meant if f is Boolean taking values +1 or -1, then the difference will be 1 or -1 if it is different and 0 otherwise. Yeah. So how do I get one measure combining all the things? So let's just average over all the x's. So this thing is called the influence. Influence j of f, it doesn't depend on x. It is I just take the L2 norm squared of this derivative and divide by 2 to the n. So this is 1 by 2 to the n, sum over x, djf of x square. So this is called the influence of the jth variable on f. Okay. So maybe one example. So this one, by the way, is not for necessarily for Boolean function. So when f is Boolean, influence j of f is really the probability that the decision changes if jth voter changes vote. So when I say probability, when assuming, so this probability is everyone voting uniformly. Independently and at random. So imagine everyone is just casting vote at random to one of the two candidates and independently of each other. Then this, what is this? This is just the number of those situations in which jth voter makes a change. So it is the probability that the jth voter's vote actually changes the decision. A kind of question which is often asked, how does it matter if I go and vote, etc. So this is what is measuring your influence on the overall decision. Okay, so maybe one example. Let me just see what. Yeah, so let's say f of x is is of x. S is some subset of. Let's take one of these characters. So what is dj f of x? So you remember this is just product xj j in s. So what is dj f of x? Okay. So dj f of x is this. So you set the jth coordinate to be 1 and jth coordinate to be -1, take the difference. Now it is kind of clear that this will be 0 if j does not belong to S. Right? If j does not belong to S, then putting that will not make a difference, right? So what if j belongs to S? If j does, if j does belong to S, then what is djf of x? Just for simplicity, let's say S is 1 to up to k. There is no loss of generality in it. So what we are looking at is x and j is 1, let's say. So we are looking at x1, x2, xk. That is our function, right? So when I want to take j equal to 1, so d1 f of x, I have to set x1 equal to 1. So I will set 1 times x2 up to xk. And then I will set -1 times x2 up to xk. And then I will subtract this thing from the other one and divide by 2. So that will just give me x2 up to xk. Okay. So dj f of x will be actually, so dj, this chi s will be, if you see what is this, it is just chi s minus j. Is clear? I mean, if I take 1 here, then that 1 drops out. This is just the chi s of x, where s is 2 to k. You have just dropped the index which is being with which you are differentiating. Is okay? This is the usual way you differentiate, right? I mean, so if you differentiate x1, x2, xk with respect to x1, what do you get? You just get x2 to xk. Formally, it's exactly the same. So you just that one disappears, right? So dj for chi s is actually chi s slash j if j is in s. Otherwise, it is 0. So what is the influence of the jth variable there? Obviously 0 if j is not in S, and if j does belong to S, it is actually this. And this, what is the L2 norm squared of this? This is of absolute value 1. So this L2 norm squared is 2 to the n. So is 1 if j does belong to S. Is that correct? Yeah, indeed. Yes, that's what it is. Because the L2 norm squared, if you look at the definition, the L2, this is of absolute value 1. L2 norm squared will be 2 to the n, and you are dividing by 2 to the n, so you get 1. You also see it, this is a Boolean function. What is the probability that chi s will change if x1, x2, xk, if the first voter changes mind, what will happen? And everyone else remains the same. This will change sign, right? From 1 to -1 or vice versa. So it will definitely influence. So this is an example of influence.
So would you define stability in terms of these influences, like lots of people are small, all people are small influences or something like that?
It is related. That's not the way it is defined. It is defined saying that if many people change, if a small proportion of people change their mind, what's the probability that yeah, in a way, this is, yeah, it's a bit like this, but stability is often defined by what's the probability that the decision will change with if an epsilon proportion of people change their mind. So maybe I can just, since you mentioned it, I can just define it. I may not use it. So for epsilon in 0, 1, let's make it delta. So one way, so the stability function is defined as, okay, so let's take a Boolean function. It is plus minus 1 is the probability that fx not equal to fy. Where what is this y and x? So x is first of all here random. So independent random voters. That's what this probability refers to. Okay, independent plus minus 1 votes. And y is, so what you do is with probability 1 minus delta, so yi for each I. Yi is xi with probability 1 minus delta, and let's even have another x dash is an independent copy of this. Okay, and xi dash with probability delta. So in other words, each person with probability 1 minus delta sticks to their vote, and with the remaining probability revises their vote, maybe again plus minus 1. Okay, so that is what stability is defined as. I am not going to use this concept, so I use some probability here. If people did not follow it, it will appear in a kind of hidden way, but I will not use it much. So, but this is the way stability of a function is defined. What's the probability? It will change if a delta. So in basically what happens here, each coordinate stays the same with probability 1. In fact, it stays the same with probability 1 minus. So yi is actually equal to xi with probability 1 minus delta by 2 and minus xi with probability delta by 2. See, the way I have written here is yi, each coordinate stays with the same vote with probability 1 minus delta, and with probability delta refreshes his or her mind. But when you refresh your mind, with probability half, you may go back to the same decision, and with probability half, you may go to a new decision. So that's why yi is actually equal to xi with probability 1 minus delta by 2 and minus xi, the opposite decision, with probability delta by 2. So that is what you do. And when delta is small, you think of delta as a small number. So a small proportion of voters are changing their mind. And this is all happening independently of each other and all that. And then you ask what will the decision change? And that probability is somehow a measure of the stability of the function. Okay, so that is a measure of the stability of the function. So one can do it for the dictator function, which is and for some other functions and see it. But what I wanted to introduce now, it's kind of close to end. So let me introduce one more concept, which I will elaborate on next time. Or maybe I tell you what is the application we are going to do, rather than try to introduce the concept. Let me try to give a preview of what it is we are going to do. So the application that we will be doing is the following kind of question. See, here when you are deciding between two candidates, where is it? There are two candidates. This is the way we are going to do is each of them vote, and some Boolean function is used to arrive at the final decision, right? So we take x in z2 to the n, the votes, and then map it by some function f to fx, which is in -1, 1, the decision. This is the decision. This is how you arrive at a decision. So the question that we will be, so this seems reasonable. Of course, you can ask which function I should use, and then you can come up with some criteria. What are desirable things that you want? Okay, so there are many desirable things you might want. For example, I mean, so what would be desirable properties here? So you can come up with choose f based on some desirable properties. So what are some desirable properties? Example, f is monotone. So f of f is monotone is perhaps an important this. That is, if x less than equal to y, then fx should be less than equal to fy. Meaning, if more voters vote for +1 in y, so xi, this just means xi less than equal to yi for all I. So whenever xi is +1, yi is also +1, but when xi is -1, yi may be +1.
It's 1 o'clock.
So more voters vote for +1 here. So then the decision should also go in the same way, etc. Right. So there are some desirable properties one can put down here, which let's not discuss. What is it that we want to do is how to do it when we have three candidates. So when we have 3 candidates, how should be the voting to decide one particular winner? Okay, so there are 3 candidates ABC. How can we decide between them? So one of the possible ways is you do pairwise elections. So let's say A versus B, an election. B versus C, an election. C versus A, an election. And then try to put those decisions together to arrive at a decision. Can we do that? What are the problems? That is the application we are going to go into. Okay, I will stop here. So I didn't do anything of content much today, but there will be more next class.